In this problem, we're being asked to evaluate an integral. The integral involves a polynomial times the square root of another polynomial. I don't see any way to algebraically simplify this. Maybe I could rewrite the exponent as a 1/2 power, but I cannot distribute that 1/2 across the 2x cubed and the 8. So it would be difficult. There is no way to rewrite this so that I can just use simpler exponent antiderivative rule. So it looks like this is a candidate for substitution. Again, when you're selecting something for your substitution, you want to choose whatever was the inside on the chain rule. This was a composition of two functions. When somebody differentiated a function and ended up with this, what probably was inside is what's in that root. This is just a general rule of thumb, but it's a good one. If you do have a set of parentheses in your problem someplace, one place to look for what to try for u is within those. And then once you make that selection, the du is a calculation. Differentiate your u, so that would be a 6x squared as a derivative of 2x cubed and nothing from the 8, and then attach a dx. This is multiplication by a dx. Now our goal is to rewrite this original integral in terms of the new variables u and du. When we're done here, we can't have any x's in our problems, just numbers, u's, and du. Part of this process is very straightforward. Where we selected u, we can replace real quickly. This 2x cubed minus 8 to the 1/2 now is simply a u to the 1/2, since u was 2x cubed minus 8. What I've got left over here is a 2x squared dx, and so I pretty much go shopping for 2x squared dx. I see an x squared and a dx right down here in this du problem, in this du equation. So if I do a little bit of algebra here, I think I can build my 12x squared dx. And when we need to do a little bit of algebra on that piece, I refer to this as a type 2 integral. It's just a little reminder that there are various types of substitution, different algebra that can come up, and this particular type is one of the more straightforward ones. You simply build up what you need from this equation. Not too bad. Anti-differentiating requires me to increase the exponent by 1, multiply by 1 over the new exponent, so that'll be a 2/3 out front, and we don't want to forget to add our constant. And then we'll make one more pass through here, clean up the constant. 2 times 2/3 is 4/3, and replace u by its original expression in x, so 2x cubed minus 8 to the 3/2 plus c. This is my answer to this problem. And again, that's a fairly complicated process, so it's a good idea to get into the habit of checking our answer. We will find the derivative of our answer, the 4/3 2x cubed minus 8 to the 3/2 plus c, differentiating all that. Derivative of the constant is 0, but what I should get when I differentiate all of this again is the original integrand back. Our goal was to find the set of functions whose derivative is equal to that integrand, so our derivative should come out to be that. I'm going to need a chain rule on this derivative. I'll pull the 4/3 out of the way, bring the exponent down, leave what's inside alone, reduce the exponent by 1, 1 less than 3/2 is 1/2, and then multiply by the derivative of the inside. That'll be a 6x squared. And the constant again is, derivative is 0. So my derivative is this expression, and I'm just going to clean this up a little bit. The 3's cancel. The 4 divided by a 2 is a 2, so this will be a 2x cubed minus 8 to the 1/2 times a 6x squared. And now I'll just gather like terms together again. The 6 times